Okay, so we are moving into the lecture 32 and we will continue with bilging and so we will most probably finish up the bilging section today. Now, as we have explained, there are a couple of different ways in which you can have the bilging. You can have bilging that occurs in different parts of the ship. In all our simulations so far, we have considered bilging to be occurring in the midship compartment of the ship. That is definitely one possibility. You have the bilging occurring in one compartment which is a distance which is smaller than the length. If you have the total length of the ship as length between perpendiculars, you have a small length which is between some two fixed stations. You will have a compartment which has the flooding in it, and bilging occurs only in that compartment. Then another possibility is that you can have the bilging at different other sections of the ship. For instance, you can have bilging in the front the front part of the ship, that is the bow region of the ship. You can have bilging occurring at the aft region of the ship, and as you can imagine, as this happens, when you have the flooding occurring in different other regions of the ship will, in case the flooding occurs at the front part of the ship, that is in the bow of the ship, if some compartment there gets flooded, then the ship will trim by the trim forward, and of course, by what we mean by trim forward is, that is the draft in the forward section of the ship will become more than the draft in the aft section of the ship. So, like if you consider this to be the ship will, if this is the front and this is the aft of the ship will trim like this. So, this is what happens if this compartment is flooded. You can look at it anyways. You can look at it as one possibility is it is an increase of weight. As we have already explained, the analysis for flooding is usually done using two methods. One is using the method of added weights and one is using the method of loss buoyancy. Both the methods are exactly identical in the sense that not identical in the method of calculations, they are of course different, but they are identical in their result. So, you get the final, for example, if you are considering the righting arm finally, you will get the same result whether you use the method of added weight or the method of loss buoyancy. So, if you consider the ship to be, if you consider this problem of flooding using the method of added weight, you can see what happens. The ship is initially on even keel. I mean, I have already described that when you say something on even keel, it means that the water line is horizontal. So, initially if the ship is on even keel or any other trimmed condition, suppose that one compartment in the bow region of the ship gets flooded, what will happen is that that region of the ship will, so there is an increase in weight in that section of the ship and the ship will trim by the forward. So, the front part of the ship is actually going down, as you can see it will be like this now. Now, so that is another kind of problem, and that is one of the problems that we will consider today. And as we have already described, there is another possibility that, I mean, I just mentioned it briefly. Another possibility is that the ship can be flooded not exactly midships, means not like this, not exactly along the center line. So, if you consider it symmetrically flooded, means the port side and the starboard side are evenly flooded, or we say that the amount of water that has entered on the port side is equivalent to the amount of water that has entered on the starboard side. If it is like that, then it is one class of problems, but a second class of problems occurs when the ship gets flooded on one side completely. That is, if you have the center line and means if this is the ship, if you have a center line, suppose the flooding occurs only on one side of the ship, maybe the starboard side of the ship. Now, if you have a situation like this, then as you can see, first of all, as the ship gets flooded, the draft will increase. So, that means the ship will sink first of all, and when this happens, the another thing that happens is, imagine, you can now see that this is not exactly the centroid of this water plane, it is not on this, because some volume is lost here. If you consider the method of loss buoyancy, some volume is lost here, but you have this volume. So, therefore, the centroid shifts to here, shifts to somewhere away from the center line at some distance h from this end, which is not equal to this b by 2. If you consider the total breadth as b, this is b by 2. So, now this distance is distance h from this edge, which is greater than b by 2, and when this happens, you will have heeling. It is unsymmetrical about the center line now. The weight of the ship is unsymmetrical about the center line now, that is, there is more weight on the right side of the ship compared to the left side, or if other way around, depending on which side is flooded. When this happens, therefore, that side of the ship will heel. So, if there is more water coming here, if that side gets flooded, the ship will heel like this. So, this let us consider this problem first, then we will go into the problem of trimming. So, both are, they are just different ways of looking at the problem, different possibilities that can exist. Now, if you consider flooding, this is what I talked about in case of, so if you consider this to be the ship, so this is the whole ship, and as you can see, one compartment has got flooded here, one this white this blue line, blue color is indicating water. So, this gets flooded. Now, as you can see, it keeps getting flooded, and it can, of course, if there is damage, this depends upon the ship's damage condition. Because of this, this whole region is getting flooded. So, one by one different compartments are getting flooded, and as this keeps continuously happening, what will happen is that the ship will start trimming about the forward. So, ship will trim about the forward, and that condition, that is the secondary condition that we will simulate today. So, first of all, let us consider a ship, let us consider a box shaped vessel. So, let us consider a box shaped vessel of existing at a waterline W0 L0, and it is at a depth draft initially of d initial, it represents the initial draft. Now, let us consider, this is the elevation view, or what we call as a profile view. Now, if we look at, so this length becomes the length of the ship, which is capital L, and this is the draft. And now, let us consider that a small region gets flooded in the center. So, if you consider this to be the center midship, if you can, so as I have already told you, midship is represented like this. So, if you consider the center, if you consider the midship and consider the flooding to occur symmetrically about the midship. So, some region has got flooded to some height greater than the draft. So, it is flooded initially. Then let us look at its plan view. So, this is again the length of the ship. So, this represents this is again the length of the ship, and this represents now B, this is B, this distance is B by 2, this is B by 2. Now, this problem is designed in such a fashion that it allows for the particular case that we talked about. So, it is flooded at the midship, all right, but it is flooded at one side, it is not flooded along the means this region is flooded. So, if you have a ship, it is the, if you consider this to be the center line. So, you have the ship like this, this is the center line, it is flooded at the midship, all right, but it is flooded at one side. So, in one, if this is the ship, this one corner here is flooded. So, extending over the full depth of the ship, of course, but it is flooded in one side. So, like this it is flooded. Now, let us consider its dimensions to be B, this is the breadth to which it is flooded, and let us consider its length to be L, this is this length L, and now if you consider the let us say that, as I have already explained, this initially the ship is at the upright condition, and in that case this is the center line and this will be G, the position of the center of gravity. Now, the position of the center of gravity does not change, because from now on all the calculations will be based upon the method of loss buoyancy, and but as a result of the remember, a method of loss buoyancy implies that volume is lost from the ship. Automatically it assumes that area is also lost from the ship. Therefore, the centroid of this water plane area is now not going to be at the center line there at G, but it is going to be here at a distance, maybe let us call it y, at this point. This height is, let us call it h. It is the distance between the one side of the ship, this side of the ship, and the position where the ship has its centroid. So, this is the final condition. Now, how will you get h? It is very easy to get h. H can be defined as the moment of area. We can do many things. We can calculate the moment of area about the about some center line. It can be about that where that b by 2 line, the region where it can be about the line where that G acts initially. So, along that line is a possibility, but easier because of some reasons. First of all, because we are calculating h from one side, let us calculate all the moments use about one edge of the, this is a rectangle. So, a one edge, let us take the moments about the edge. Therefore, h is defined as a moment of area about the edge divided by the total area. Now, the moment of area, remember there is, what do we have here? First of all, we had a complete rectangle. So, this L into B, we had a complete rectangle, and of which, because of flooding, some volume is lost in one corner, some volume is lost. Some volume is lost directly implies that some area is lost in that water plane. So, if you take that water plane area, initially you have L into B, and finally you have L into B minus some area here. This area is again small l into small b. So, that much area is lost, and so that we need to figure out. So, based on that we get the moment of area about the edge divided by area, we will get h. So, you will get h to be L into B, and its moment is, means here you have L into B, this is the whole area, and into the position of its center of gravity, which is b by 2, this is b by 2. So, L into b by 2 minus, now a small area is gone here, this is of length small l, it is of breadth small b, and its centroid is at a distance of small b by 2. Therefore, its moment is L into b by 2 divided by the total area, which is L into b minus L into b, small l into b. So, this will give you your h. Okay, this gives you this distance h, which is the position of the new centroid. This is where the new centroid occurs. The initial centroid is here, and that is when the ship was in the watertight condition without the flooding. When flooding occurred, the note again that the G, which is the center of gravity, has not shifted, but it is only the centroid of the area has shifted to a new point. Now, why do we need the centroid of area? We will see in the next figure, we will draw it. So, this becomes h, and now okay, then let us draw the other one. Now, we have always drawn sectional figures, cross sections, means if you have the ship like this, you make a section like this. So, we have already drawn these sections, which in the lines plan we actually call it as a body plan. The body plan section will give you the different stations and all that. Now, just like that, if you draw the this is a box shaped vessel. Now, for this we are drawing the so this is the section. Now, let us consider this to be the initial water line. Actually, usually you okay, this is okay. This is the initial water line and the final water line, and initially the ship is at G, that is the, it is at midship section, this is at G, I mean this is at the mid, again the midship. So, this is G, somewhere here you have G where the weight of the ship is acting, and now what has happened is, in this case as you see from this side some area or volume has gone. So, what will happen? The ship will tilt in this side, and as a result the water line will tilt up. I mean the ship will, the water line will, the ship will tilt in this fashion up, that means the water line will come down like this, water line has come down. So, initially the water line is here WL, W0, L0, and the ship has tilted in this direction. So, water line has tilted into W1, L1. So, this is tilted by an angle phi, and as a result now the first of all the position of B will shift here to some new point, that means some volume is lost from here, which implies that it is equivalent to saying that some volume is added on this side, or what it means is if some volume is lost here, we know that the center of buoyancy has to shift here. So, B shifts to this point B1, and there will be, and if you draw a vertical to that, no you sorry here. So, if you draw a vertical at G, you get the meta center which is MB, the so this will give you the position of the meta center, and the distances, let us call this, let us draw a perpendicular from G to Y. So, G to this point Y, let us call this distance as x, or at least GY, the distance GY, as you can see is the distance between G and the new position of the centroid. This is what we did in the last time, just previously we saw that we need to find the position of the centroid, and the position of the centroid is required for this purpose, that is to find the distance between G and the new position of the centroid. So, that distance is measured as GY. So, we get here GY is actually equal to the GY here, it is H minus B by 2, you can see here. How do I get this? Just look at this, this is Y here coming here. So, this distance that I am talking about GY is H minus B by 2, this is H and this is B by 2. So, H minus B by 2 is the distance between G and Y, it is one thing we need. Then other things we need is one KB, we have to find the final KB of the ship. We always say that KB is the vertical height of the center of buoyancy, vertical height of the vertical distance of the center of buoyancy from the keel. Now, that distance is always measured as half the draft, whatever is the draft. So, it is dB divided by 2, this will give you the KB. Now, another thing we need to calculate is Bm, in this case Bm, which is equal to defined as I by V or I by del. I by del, that is the metacentric radius, is defined as B1 MB is equal to I by del. Now, the only slightly only thing you have to know here, probably here or slight catch here is in the calculation of I, to know, note that your I now finally. So, what do we had? What did we have initially? We had a whole box. Now, what happened? It got flooded on one side, as a result of which one small volume got lost here. Now, what are we finding? We are finding the I, which is the moment of inertia of the water plane area. So, when you are finding the moment of inertia of the water plane area, then in this case this much area here is lost. So, you are actually have to find the moment of inertia of the rest of the area, which is equal to the moment of inertia of the whole area minus the moment of inertia of the small region. So, that is very easy, but it is still important. It can be calculated very simply as LB cube by 12 minus LB cube by 12. So, this is about the B by 2 line. Now, in this case it is just easier to do all the moment of inertias about the one side of the box. Therefore, we say that I is and if you remember the formula, the moment of inertia of a rectangle about a edge of the rectangle is usually given as represented as LB cube by 3. It is equal to LB cube by 12 if it is about the center line, it is equal to LB cube by 3 if it is about an edge. So, LB cube by 3 minus LB cube by 3. This is the moment of inertia of the whole rectangle now about an edge, means which edge? This edge, this edge. So, it is a moment of inertia about this edge. So, we have now note that we always need the moment of inertia. Now, in the derivation of Bm equal to I by del, that Bm metacentric radius was derived using the assumptions, we have done all these derivations, that derivation of Bm del assume that I is always the I about the centroid of the water plane area. That means, in this case you need to calculate this I about the centroid as well. Now, you know by the parallel axis theorem that once you have the moment of inertia about one edge, if you can just do I about that point minus a y square will give you the moment of inertia of that rectangle about that new position. So, that we can calculate using the parallel axis theorem, which proceeds as this. So, I about the edge point or the centroid will be equal to this I, which I have just written here, I minus a into h square. This will give you the this I is actually the I about the side. So, this will give you I about the edge or I about the that line through h, the position which is at a distance h from the side. So, from that you will get Bm equal to I by del. Then once you have that, let us look at this figure. You see that if it is tilted through an angle phi, from this you can directly read that tan phi is equal to Gy divided by Ym, Ym or Ym in this case. Gy we have already calculated, it is equal to h minus b by 2, which is the distance between the just that distance between the g and that the vertical position of m or the projection of m, the position of the projection of m. So, that gives you Gy divided by Ym. Okay. Now, therefore, once you have that you get Km is equal to Kb plus Bm, Ym is equal to Km minus Kg. Let us look at this figure Ym. Okay. Why is it so? Because remember this will be the keel. So, if you are looking at the vertical distances, Km, this vertical distance is the same as this vertical distance. So, this is Kg. So, this is also equal to Kg. So, Kg Ym Yg or Ky is equal to Kg. So, this Kg is actually equal to Yky, which is equal to Kg. Because of this you can get this expression. Now, we know all these things, Kg we know, we have to know Kg, there is no way to calculate it. Kg is the center of gravity of the ship or the box shaped vessel, the vertical position, that needs to be known, and Km has to be known from hydrostatic, and this is a box shaped vessel anyway. So, you know you can use the formula that Km is equal to T by 2 plus d by 2 plus b square by 12 d, that is a known formula for box shaped vessels, where d is the draft of the ship, draft of the vessel, and when you have that you can get it as d by 2 plus b square by 12 d, that will give you the km, or in case of if you are dealing with a large scale ship, the value of km will be given from the hydrostatic data. So, from the hydrostatic data or from the hydrostatic particulars, you get hydrostatic curves, you get the km value. Kg value has to be known, it has to be given, it has to be given by in the problem itself, and once you have that, you find Ym, as we have seen Ym comes as kg itself, then no Ym Yg is equal to, I mean ky is equal to kg, and as a result you get Ym, the distance between y and the meta center, as km minus ky. So, that once you get that, then you can just use the formula that tan phi is equal to gy divided by Ym. Now, that will give you phi, which is the angle of heel. Therefore, in this particular case where we had a ship which is now flooded at one. So, you have the ship which is flooded on one in the midship section, but along on one side, close to one side, it is not flooded in the center line, it is not flooded symmetrical to the center line, but it is flooded on one side. When this happens, the ship initially sinks, as a result of which its waterline goes up and the draft increases, and then the ship heels. Okay. Depending on which side goes down or which side gets flooded, depending upon that side will go down, and either way you look at it, that is either the if you look at it in case of weight, you see that weight has increased there, so it has to heel there. It comes as one of the many problems that we have done in the shifting of weights. In fact, the inclining experiment itself was devised using this, that is, you shift a weight from along the deck, you shift a weight from one side to another, you see that the ship heels in that direction, and then you calculate the heel and the horizontal distance of the center of gravity moved and the GM, that is the inclining experiment. Now, so just like that, in this case the ship gets flooded, so additional weight comes, let us say, on the right side, and because of that the ship heels to that side, or if you look at it the other way around, ship loses its volume there, it is still the same thing, ship heels again to the right side. Okay, either way, then so this explains one type of problem dealing with the ship's flooding. Now, we will look at one problem as such, that is, you can have, suppose you are told that there is a box shaped vessel of length 60 meters, breadth 9 meters, and it is floating at a draft of 5 meters, and it has a kg of 3 meters. You are asked to find the list if a midships compartment of length 6 meters and breadth 6 meter is bilged. Therefore, it is a midship compartment, therefore, it is occurring at a in the midship, but it is, the problem says that it is occurring, the problem is not it's, but the figure is given along with the problem, which says its problem is something like this. So, if you look at the just like I explained the previous problem, it comes something like this. So, you have the center line, and in this case the ship, a midships compartment somewhere here, a region is flooded, and the breadth of the ship initially is 9 meter, this is 9 meter, and a breadth of 6 meters. So, something like this, one compartment like this, of 6 meters. So, this is of breadth 6 meters. So, out of the 9 meters, 6 meters length is, this region is flooded. Now, this is the same problem that we have done. First of all, we need to find the position of the centroid here somewhere, as you can see, more volume is lost here, and directly more area is lost here. If area is lost here, area is still available here, we see that the centroid should shift to here, it will shift like this. So, centroid will shift like this. So, from this point it shifts here, and this distance we have called as h, as in the previous derivation, this is h, and this is b by 2. So, this is b by 2 and that is h, and Now, the question is to find the list. So, because of a flooding like this, because of the ship flooding like this, it is seen that the ship first sinks and then heals, just like I said. So, let us see how this problem is to be done. So, first of all we need to find, we use the formula intact volume before flooding equals intact volume after flooding. So, this is the most general formula, intact volume before flooding is equal to the intact volume after flooding. Intact volume before flooding is LB di, length breadth into the draft initially, equals LB dB minus LB dB. So, this tells you the intact volume after flooding, which is LB dB, capital LB into dB, which is the bilged draft, the draft after the ship has bilged, minus LB dB, small b is the compartment volume, small l represents the length of the compartment, b represents the breadth of the compartment, I mean that small region of the compartment which is flooded. So, this thing, so L into b will give you the area and into draft bilged. So, that will give you the volume of the compartment that is flooded. So, as I said before, this equation just says that, I mean what it says, that the intact volume before flooding is equal to intact volume after flooding is the same as saying the total weight after flooding is equal to the initial weight of the ship. This equation is actually the same as if the total weight of the ship after flooding is equal to the initial weight of the ship plus the volume, the weight of water added. So, it is just saying a mass conservation, it or shifted it becomes a volume conservation. So, that is this equation, LB di is equal to LB dB minus small l b dB. So, from this you get dB in this problem. Since you have L B, you are given the initial draft, you are told the L B, which is the volumes, the dimensions of the compartment that is being flooded. So, once you have all this, you can get dB, which is the bilged draft, first step. Now, we need to find the position of the H, which is the centroid of the area. So, you need to find the centroid of the area, that is based on what we have done so far, it is very simple. So, what you have here, you have area and you have its distance of centroid, you make a table like this, distance of its centroid. So, that area is there, distance of the centroid and moment. So, you have distance of the, and so initial area is the L into B is the area of the total shape, total box, that water plane, and distance of the centroid is B by 2, you find its moment. Then you have an area of L into B, in this case its breadth is given as 6 meters and length is given as some 6 meters. So, based on that 6 by 6 area, like as we have discussed here in this figure, this 6 by 6 the 6 by 6 region is flooded. So, this area is now lost and therefore, it is minus L B into distance of this is B by 2 and you calculate moment. As you know, moment is just this first column into the second column multiplied by the second column. So, it gives you this and finally, you need to find the final H, which is equal to the final moment divided by the final area. Therefore, like this will give you the final moment, this will give the final moment and this will give you the final area. So, just doing this you will give you the H, this is the distance of the position of the centroid from this edge. So, this is the side. So, distance from this side is here. So, this distance will give you the position of H, which is the centroid of the area, final centroid of the area, then remember what the main purpose of our work is to find tan phi, which is equal to given by Gy by Ym. This was explained to be the equation for tan phi. So, Gy as first thing we need to calculate is Gy, which is equal to, we have seen it is equal to h minus b by 2, and I have already described it, no need to describe it again, h minus b by 2. This will give you for this problem just we have already calculated h, which is the distance of the from the center, from the edge, from the side we have seen the distance of h, we have seen the distance of h from one edge, we have seen the distance of the position of the centroid from one edge, that is what we have measured as h. So, h minus b by 2, then we need to find I. This is one important thing. First, remember, as I have already mentioned, Bm, this is to calculate Bm using this formula. Our purpose is to calculate Bm using this formula, I by del. Del is the underwater volume, and I. So, you need to calculate I. In this, I is the moment of inertia of the final water plane, which is actually the whole water plane minus the so it is the whole water plane minus the water plane minus the small area that is lost due to the flooding. So, that whole area minus the small area lost due to flooding. So, that much area, the remaining area, moment of inertia of that about the centroid. So, it is a moment of inertia about the centroid and not about an edge or about the symmetrical center line, it is not about that, it is about that centroid. Now, to get that, as we have already seen, it is best to calculate I about one side, use the parallel axis theorem and calculate I about that h or the centroid. So, first we calculate I about the side, which is given as L b cube by 3 minus L b cube by 3. So, this will give you I about the side, then you do I about the h point is given by I about the side minus a h square. Do this, this will give you the formula. So, in this case you will get then you do Bm equals I by del, and this will give you an answer of about 1.28 meters. Now, you are given in this problem Kb 2.68, therefore, Kb plus Bm will give you Km, Kb plus Bm will give you Km, that is equal to 3.98 meters Km. Then Kg is given for the ship, it is given to be 3 meters, it is already given in the problem 3 meters, and we have already seen that Ky is equal to Kg from the figure. Therefore, Ym is equal to Km minus Ky, which is equal to you can see that 3.98 minus 3. So, this is about 0.98 meters. So, this gives you the value of Ym, and remember what we were supposed to do is to calculate tan phi given by Gy by Ym. Now, it becomes straightforward. We have already calculated Gy, which is equal to h minus b by 2. H minus b by 2 gives you the Gy, the distance through which the center line has shifted, and Ym gives you the distance between that y and the meta center. So, this will give you, using this equation we can get the value of Gy by Ym, which is equal to the tan of the angle of phi. So, you get the angle of phi in this problem to be about 6.38 degrees. So, this is one sort of problem which we work on. Now, we move into the second type of problem that I mentioned at the beginning of this lecture, that is, in case like we mentioned in this, we have seen in this figure also, instead of having the bilging occurring at any of the instead of the bilging occurring at the midship compartment like right here, this is the problem that we have concerned so far deals with that. We consider that the bilging occurred in the midship compartment here. Instead of that happening, Now, we are going to consider bilging to be occurring at one end compartment, most likely in the forward side. Here it floods in the forward side, and one, of course, we are not considering progressive flooding, one side gets flooded, and that is a problem that we are considering next. Now, so in this case we have, let us consider the ship, the box, so you have the box shaped vessel, and because so one compartment like this in the front part of the ship gets flooded. So, this thing, let us say that there is a hole here, this compartment gets flooded here, this is of length small l, this is of small l, the total length of the ship is capital L. So, this compartment gets flooded. Initially, let us assume that this is the water line initially, it is, and therefore, the initial draft is d initial, d I is the initial draft, and finally, the because of its bilging, now because of this bilging, just like I explained the previous problem, in this case also something happens, that is the ship is like this initially, to it is initially at some draft. So, in the forward side of the ship one compartment has got flooded, as a result of which this compartment gets flooded, and initially the ship sinks because of the added weight, the ship sinks. So, there is an increase in draft, and then there is a in this case, since this side has now more weight than this side, because of this unevenness in weight, this will trim like this. Okay. The ship is going to go down at the forward side. So, the front part of the ship will trim now. So, this is the new process that we are trying to mathematically study here. Okay. So, initially the draft increases to dB, and then the ship trims and it goes up, the draft increases to dF. So, the draft, final draft is now dF, that is the that water line is now, let us call this to be W1 L1, this is the final water line, where the ship has finally the ship has come to this position. Now, we will have here G, this is the position of G, the centroid initially, then at initially at G, let us assume that the ship initially it is B0. Now, because of its trimming, now the B shifts to it is a loss of buoyancy. So, the B is now here. So, this is B1 or B2, I will call it. Now, so the final position of the center of buoyancy is B2, and M is the position of the meta center. This is the same explanation as in the previous figure, weight of the ship acts here W. So, B1 is the position of the center of buoyancy, B2 is the position of this B2 in this is the position of the center of buoyancy. Now, same method as we did, if you take that the distance through which the same concept, that is in this problem the only difference is that we had last time we had one in the last problem we considered that one area is lost on one side, as a result of which that center line shifted to slightly above slightly higher, slightly the other side to the starboard side. Now, in this problem, instead of the center line shifting like this, we are talking about G shifting here. Okay, it is this shift, it is no longer this shift, but it is this shift now. Now similarly, so this area here, this is flooded. Okay, this part of the ship is flooded. So this out of this, some area will be lost in the front part of the ship. So how much distance does it shift to the same way, that is, you take the moment of the area divided by the total area. If you take the water plane area, remember water plane area will be like this. So if you take, so if your water plane area will be a section like this. So water plane area will be like this. Now at that point you will have some area lost here. So by doing that we can find that it is very easy. If you take the moment, you will see that if this is shifted by L and if you assume its centroid to be at L by 2, you will see that the this will be shifted by L by 2. So this will be the position of the, so the distance of the centroid. Now let us call this to be the aft perpendicular. So the distance of centroid from aft perpendicular is given to be L by 2, which is this is L by 2, this distance. As you know, this whole distance is L, this is L by 2, this distance from here, and therefore it is L by 2 minus L by 2, small l by 2. Okay, so this will give you the distance of the centroid from the aft perpendicular. Now as you can see in this figure we need. So as you can see in this figure, the distance of G from the aft perpendicular is again equal to L by 2 always, because this is again the method of lost buoyancy and the center of gravity remains at G. Now the only thing we need to do here is let us consider the weights acting now. Okay, so consider this. So what do we have? We have so about this new position of the centroid, that is what we call as a center of flotation. The center of flotation is now here. Remember, center of flotation is defined as the centroid of the water plane area, and in this case some water plane area is lost in the front, because this side is trimmed, this side is bilged, and because of this bilging some area is lost here. Because this area is lost here, the water plane area, the centroid of the water plane area shifted here from the center, from here it shifted here. Now this is the center of flotation, and if you take now moments about the center of flotation, we see that at G, which is the position of the center of gravity, there is a weight W acting downwards. Okay, and the position of the center of buoyancy is here. So there is no weight acting upwards, it is along that same axis. So the net moment that is acting, which is trying to cause the trim, is this W, the weight of the ship, into L by 2, which is small l by 2, which is this distance. So W, the weight here, this W into small l by 2, this much is the moment causing trim. So we write the trimming moment equals weight into L by 2. This is your trimming moment, which is W into L by 2. Or now once you have the trimming moment, how do you calculate the change in trim? That is very easy, we have already done many times. The change in trim equals the trimming moment divided by the MCTC, moment to change the trim by 1 centimeter. So change in trim is equal to trimming moment divided by MCTC. Now the trimming moment is W into L by 2 divided by MCTC will give you the change in trim, which we usually write as trim T, or change in trim. Change in trim will be given by W into L by 2 by MCTC. This will give you the change in trim. Now just like before, once you are able to find the total change in trim, you need to find the change in trim aft, change in trim forward, same way, same equations. That is, if I mean in the previous chapter, not here, here we have used different notations, please do not get confused between small l. In our previous chapters, that is the chapter dealing with trim where we were doing, the small l actually represented the distance between the aft perpendicular and the center of flotation. So, that is small l. If that is so, then the change of trim aft is given by small l, which is the distance between the aft perpendicular and the center of flotation, divided by capital L, which is the total length of the ship, distance between perpendiculars, multiplied by the total change of trim. So, that will give you the change of trim aft. So, L by small l by capital L into. So, in this case, just in this case, remember small l represents not the distance between the aft perpendicular and the center of flotation, but it represents L by 2 represents this distance, small l represents this distance. So, this is L by 2. Now, but the concept remains the same. To get the change of aft draft, I need to find the distance between aft perpendicular and the center of flotation. Center of flotation is this. So, it will be L by 2 minus small l by 2. So, L by 2 or L minus small l by 2 into L into change of trim, this thing. So, L minus L by 2 L into W into L by 2 divided by MCTC. So, this will give you the total change in trim in the aft side, and if you want to find the change in the trim in the forward side, the instead of L minus L, you using the previous notations, if L is the distance between small l is the distance between the aft perpendicular and the center of flotation, you what you do is you do capital L minus small l divided by capital L, that will give you the distance from the, instead of taking this distance, you take this distance, the front distance, that will give you the distance, that will give you the change in trim in the forward side of the ship. And once you find the change in trim forward, change in trim aft, what you generally have to do is you change whatever is the initial trim, you add this final trim, add this change in trim aft to the initial trim aft, and you will get the final trim aft. Change in trim forward to the initial trim forward, will get the change, you will get the final trim forward, and that will give you the final drafts also, that will give you the final draft in the forward and the aft section. Okay. So, this is, we have explained now two types of dealing with the bilging problems. Any kind of bilging problem will be having, I mean now that we have done two extreme types of problems, means we have studied the case when the ship can heel, and we have studied the case when the ship can trim due to bilging. These are mainly the two types of process, and of course, you know that you can just extrapolate this to say that if you have a time dependent bilging, means as the time goes on, the flooding keeps continuously happening, and if you are trying to study that problem, then of course, it does not become healing as such, it becomes a case of rolling, it becomes dynamic process and not a static study. And since this course is on hydrostatics, we are not dealing with the dynamic process of flooding, though it is definitely a very important point and a very important topic. It is a very very active study of active area of research. So, that gives you different ways of calculating the trim or the heel as a result of bilging. So, these are two extreme cases when you have bilging in the front part, of the section, this gives you that how to find the trim, and in case you have bilging occurring on one side of the ship and not the other side, that gives you another way of calculating the heel. So, you can combine the two to calculate very complicated cases where you have some bilging not at the center, not at the end, somewhere in between, and the whole process becomes a combination of these two. You can get the trim and the heel due to this process and combine it and get the final value of heel and trim. It might be a combination of two and you get the value of heel and trim. So, this Okay, so with this I will stop here today. Thank you.